Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. In the last week we have seen the variants of CNN, and in this week we will be seeing the explainable AI, the concepts, techniques and then the implementation. The following are the contents for this particular week. We will first see the introduction of explainable AI. What exactly is explanation in AI? We will also look into what are the different techniques of explainable AI and what are different methods. And the following are the different methods that we will be exploring in detail. And towards the end of this particular week, we will see the hands-on implementation of XAI methods. Topics for today's session. We will first see the introduction and we will look the first two methods, that is PCI and occlusion, in detail. So, before we get into the methods, let us try to understand what is the need for an XAI. Now, when you look into, there is an input and the input here is an chest X-ray that is passed to a neural network. And what neural network that we are using, since it is an images, we will be passing it to a CNN model. Now, when it is passed to a deep neural network, what a neural network will do? It produces the output. And here the output what it has produced is an accuracy of 98%. But here we do not know. We do not know why exactly we got this 98% accuracy. We do not know why model has given this particular prediction. Suppose here it is a chest X-ray with pneumonia and without pneumonia. Suppose if you have passed an input image with pneumonia and if the model has given us 98% accuracy, there is a question that why the model has predicted it as a pneumonia. That is the first question that we have. And the second, we do not know which region in this particular X-ray that the model has looked into. We doesn't know even this. And the third, there is no provision. We cannot even verify that model has really looked into the medical features only or whether it has looked into some artifacts. So, we do not have an answer for any of these questions, and all what we know is we have an accuracy of 98%. This is a limitation. Limitation of what? Limitation of this neural network. Which neural network? Here we have used CNN. Despite we got this 98% accuracy, many of the neural network models are often referred as a black box system. What exactly is a black box system? These neural networks operates in such a way that it is not easily understandable by humans. So, this is what exactly is the problem with the neural network. And even though this model achieves very high accuracy, there is a lack of transparency. Because of lack of transparency, what all different issues that we are seeing? There is an issue with the trust. There is an accountability issue, fairness and then ethical use. What is a trust here? Now, because it is a medical application, can a doctor really trust AI's output? This is what is the trust. And accountability here is, now AI has made the prediction. What prediction it has made? The model is 98% confident that the given input is pneumonia. The input that is passed, it is classifying it as pneumonia. But what if it is wrongly classified? Who is held responsible for this? So, this is what is an accountability. And fairness, the meaning of fairness here is, does the system treat all the groups equally? Can it treat every group equally here? That is the fairness. So, all these are certain limitations when it comes to a neural network, because it is treated as a black box. Because of this limitation, we have to move to an XAI. Now, what exactly here? Now, we see there is an input. This input is being passed now to an explainable AI. Now, when an input is passed to an explainable AI also gives us the output. But here, along with the output 98%, look very carefully, it is also giving us the reasoning here. So, when an input is passed to an explainable AI along with the output, that is 98% accuracy, it is also giving us that which are the regions that the model has looked into in order to give this particular prediction. So, here for a pneumonia, the model has focused on this part of the input image. For this particular without pneumonia, the model has looked into this portion of an image. These are the features or the pixel values which has contributed. So, what exactly has happened here? If you look into this, it is just a prediction only, but here it is a prediction with reasoning. So, here what we are getting a visual reasoning that exactly aligns with human expectation. So, this shift from prediction only to prediction with the explanation is something which is very essential for building the human trust. Thus, it is meeting the regulatory requirements and it ensures there is an ethical deployment of AI. So, this is the main motivation behind AI, because although the neural network is giving us the very good accuracy, very good performance, but they lack in transparency. So, if this is the advantage of explainable AI, then where exactly we use explainable AI? Explainable AI is mainly used for an high stake applications. For example, if you take a medical diagnosis, or if you take an autonomous driving vehicles, fraud detection, or it can be any judicial decision making, where any incorrect predictions cannot be tolerated. If it is having an serious consequences, then it is always good to go for an explainable AI, because it is also giving us the reasoning why it is making the prediction. So, this is the motivation behind why one has to go for an XAI. One of the most fundamental question, what is an explanation in AI? So, if you look into, we have an ovarian cancer data set, and here we have many samples like S1, and we have samples like S2. Now, our aim here is, when we pass this sample to a neural network here, the model should predict whether a given sample is benign, border case, or malignancy. This is what is the problem statement that we have. So, when S1 is passed, when a sample, first sample or S1 is passed to a neural network, the model is predicting it as benign. And when a second sample S2 is passed to a neural network, the model is predicting it as malignant. Now comes the question, why did the model classified S1 as benign and S2 as malignant? This is the first question which is arising. Why did the model classified it? And the second question what arises is, now there is a feature here, all these are the features, right? There are many. Now which are the features here? Which features here were most influential to get this particular decision? The S1 is being predicted it as benign. If it is predicted it as benign, which are the features which has mainly contributed? Then we will have one more question, how this output is going to change if a certain of these values are changed? How would the output change if certain inputs were modified? This is the next question that we have. And the next question is, can we depend on model's decision for this specific problem statement? Now, model has predicted it as benign. Can I really trust this output that model has given? So, all these are certain questions which we get once we see the output. So, what exactly is explanation in AI? It is basically answering all of these questions. So, answering these questions is actually an explanation in AI, and answering these questions is actually the role of XAI. explainable AI is also called as XAI in short term. And what is the main aim by answering these questions? You are making the decision process of AI system interpretable, transparent and trustworthy for human users. So, this is what is explanation in AI. Now, let us get into the most important concept, that is the techniques of XAI. We have various techniques. In that, the first technique is a permutation based method. This is the first technique. Now, what exactly is a permutation based method? Now, our aim here is we want to identify which are the features which are important for model's prediction, which features the model has looked into in order to give the prediction. This is our ultimate goal. If that is the case, which all different techniques are there through which we can achieve this? First is a permutation based method. In permutation based method, what we are doing? We are taking an input, randomly we shuffle the entire input, and then we observe how the prediction is going to change, and then we are understanding which are the features which are important. So, what are the different examples or methods which are there under permutation based? The first method is PCI, which is a permutation channel importance. Second method we have occlusion, and the third method is SHAP. All these three methods falls under permutation based method. The second XAI technique what we have is post hoc and model agnostic. What is a post hoc? The post hoc is it is a method which will generate an explanation only after once the training is completed. We have taken some neural network model, we have trained the model. Once the model is trained, now it is ready to give the explanation. That is what is a post hoc. And what is a model agnostic? The meaning of model agnostic is it is model agnostic can be applied to any models. You can apply this to machine learning models, you can apply it to deep learning models. One such example is LIME. LIME is one XAI method that can be applied to any models. The third XAI technique what we have is a gradient based method. What is a gradient based method? Now we have built a neural network. Neural network, once the training is done, during a back propagation we are going to get the gradients. Now once the gradients are obtained, then we will be using this gradient based methods. We will be using each of these methods to highlight which are the features that are important for model prediction. In short, gradient based method are those methods which will use the gradients to tell which are the features that are important. And the fourth method what we have under XAI technique is interpretability by design. And what exactly is this? There are some methods that are inherently transparent when they are built. So, for such models we use interpretability by design method for telling which features are important. Example, we have CAMs. So, what is a CAM? It is a class activation maps. So, these are the different techniques. So, under this let us look into for today's session, we will start with the first technique, which is permutation based. Under this there are three methods. In this particular session we will look into the two methods. One is PCI, that is permutation channel importance, and second we will look into an occlusion. So, let us start with the PCI. Now, here we have a data set. What is this data set? It is a data set which it is a multi-class classification problem. It is having 4 different classes. Now, because it is an image and we have a multi-class class, we are going to build one neural network. What neural network we are building? We are building one CNN model. For understanding, I have built a very simple CNN model here, but in reality we will be building an good complicated CNN model which suits to our problem statement. So, here we are building one CNN model. Now, once we build a CNN model, on this particular data set we are going to have we are going to compute the baseline performance. What is the meaning of baseline performance? On the data, original data as it is, when it is passed to a neural network, we are going to compute its performance. Say for example, on this particular data set, we got the accuracy of 90%. Let us hold this accuracy, let us save this. Then now we know from our previous sessions, whenever we take an image, especially when we deal with the color image RGB, it will have totally 3 different channels. So, this is an example. If you look, this is an original image that we have. This original image, since it is an color image RGB, we have a red component, green component and then the blue component. Now, what is the topic that we are discussing? We are discussing PCI. What is a PCI? PCI is one technique under explainable AI which tells which feature is important. Now, PCI falls under permutation based. What is a permutation based? We are going to randomly shuffle the input. Now, how it is going to do? Here we have taken a color image and there are 3 different channels. We take one channel at a time. First we have taken a red channel. We are completely shuffling the pixels of red channel only. We are not disturbing green and we are not disturbing blue. For the first time, we are taking the red channel and then all the pixels in the red channel are disturbed without actually disturbing G and B component. Then what image we are going to get is a permuted image. What is a permuted image? Image where one of the channel pixel values are shuffled. Then what we are going to do? Now we are going to pass this to a model. When you pass this image to a model, definitely we are going to get once again an accuracy. Now, if an accuracy drops, if you see here, if an accuracy drops, then we say that red channel is important. If accuracy hardly changes, there is a very small change in the accuracy, then we say that red channel is not having much importance. So, if an accuracy drops, what is that we are doing? We are taking an input image and then we are taking the channel. What channel we have taken? Red, and we have randomly shuffled it and we are getting a permuted image. That permuted image is passed to a model and then we are computing the accuracy. If the accuracy drops, what is the inference here? Then the red channel is very important. If accuracy hardly changes, then red channel is not having much importance here. We are going to calculate something called as importance of a channel. So, ICH indicates which channel we have computed. We have computed for red. So, we are going to compute red channel importance. Baseline performance was 90. After we have shuffled red pixel, we got a permuted image, and that permuted image, when we have passed to a model has given us 70% accuracy. Now, we are going to take the difference between the baseline performance and the performance after permutation of the channel. We are getting a 20. So, this is the important score for a channel red. Now, what we are going to do? We are going to repeat this. First, we have done it for a red channel and we have seen it is a 20. Now, similar step, we take a green component and then we doesn't disturb red and blue. We are going to completely shuffle the green matrix here, or the green channel pixel values, and then we are going to get an permuted image. That permuted image is once again passed to a model, and then we once again calculate what is the importance score. Here the importance score for green we are getting 5. Similar way, we then go with the blue channel. Now, blue channel pixels are completely shuffled. We are passing it to an new model, and again we are getting its accuracy, and then we are comparing it with the baseline, and we got this. So, from this values 20, 5 and 1, this 20 and this 5 and 1, what are we understanding? We are understanding that the model relies heavily on a red channel, then the model is relying on green, and barely it is depending on blue. So, this is how the PCI works. So, what exactly, a quick revision, what exactly is a PCI? PCI is one of the technique of XAI, which will tell us which channel is important. So, when we say channel, it is an RGB. So, whether red component or green component or blue component, which of this channel is important, that is what PCI will tell us. How does it works? First, we are going to build a CNN model. For this CNN model, we are passing the entire original data, we are computing the base accuracy. Once we compute the baseline performance, then we are going to pick one channel, and we are going to completely shuffle that particular channel. When you shuffle that channel, we are breaking the pattern in that channel only, but we are nowhere disturbing the green and then the blue component. Then once you shuffle this entire, once again you re-evaluate the model, and then compute what is its accuracy. Once you get the accuracy and you have a baseline, we are going to compute the importance score of that channel. So, how is that you are computing the importance score? You are computing by subtracting baseline accuracy and the accuracy after permutation of the channel. We are going to get this importance. Once you do, we repeat it for green, and we repeat it even for blue. We are going to get an importance for R, G and B. And what is the main inference here? If the accuracy drastically drops, if there is a big drop in accuracy, then definitely I value will be very large. When I value is very large, we say that the channel is very important for model prediction. If there is a very small drop if there is a very small value, I value is very small. If I value, when is that I value will be very small? When there is a small drop, or when there is no drop in accuracy, ideally we get I value very small. When I value is very small, we say that the channel is less important. So, this is how the overall PCI works, where we have an accuracy. If there is a big drop in accuracy, then we say that the channel is important. If there is a small drop off, there is no change, then the channel is less important. And let us now look into the occlusion, the second method called occlusion. Now, how does occlusion works? Let us look into this. We have an original image. This original image, once again from all our previous sessions, we know that whenever you consider an image is read by a system as an matrix, and it consists of an pixel values. Now, this is an original image, and it is an associated pixel values. Now, what is occlusion here? Occlusion is we are taking a small patch. Now, what is that patch here? Can you see there is a small patch that we have fixed here. This is the patch. Okay. Now, what is the size of the patch? That is completely user's choice. You can define the patch size of your choice. For this particular example, we have taken a patch size 3 cross 3. So, when you take 3 cross 3, in this particular patch, we are going to put all the values as 0. So, let us understand that we are going to add 0 for all of these values. So, can you see the equivalent value, because it is 3 cross 3, it is equivalent to all that entire patch values, we have made it as 0. Now, we are performing a convolution operation. In order to do a convolution operation, what do we require? We require a kernel. So, what the kernel will do? Kernel will go through the entire image. Now, when it is applied onto, when this kernel, when it is applied onto this, and when we perform a convolution operation, we are going to get 0 only. Okay? And then next we are going to do a stride. That we will see in a while. So, we are going to take a patch and we are adding all the values 0, we are performing a convolution operation and we are going to get this result. Now, once we do this, we are going to calculate the accuracy. We are first calculating the baseline accuracy. What is this baseline? It is without any patch, without any occluded patch. So, let us assume the probability that it is a dog image is 98% or 0.98. Now, after we have occluded this portion, after we have put this patch, we want to understand what is the importance of this particular patch in making the prediction. Now, when you look into this image, ideally our aim is to identify the dog. Dog is here, but the patch is somewhere here. Ideally, you will not get any difference in the accuracy. It does not make any much contribution. So, you see here the accuracy is hardly there is some difference. Why hardly there is some difference? Because this patch what we have considered is not making much contribution to predict whether it is a dog or not. So, what we are doing? We are first taking the image, we are training to a CNN model, and then we are going to get its performance, and here the performance is 0.98. The probability that it is dog is 0.98 or 98%. Then we have considered this patch, we have put the patch and then we are passing it to an CNN model, and we are now calculating its accuracy, and the accuracy what we got is 97. And what we are now doing is we are calculating delta p. What is the change? So, 0.98 minus 0.97, we are getting 0.01. So, whatever the value that we have got, now what we are doing, we are going to place this delta p value in the entire occluded patch. Here the occluded patch here is 3 cross 3. In the entire 3 cross 3, we are going to place this delta p value there. So, then what we are going to do, that is with respect to the first patch. Now, we are going to slide it. So, what did we do so far? We have taken this particular patch. So, therefore, this is where there is 0. Then we have passing it to an CNN model. We are getting an accuracy. Original we got this. With this particular patch, we got 97, 0.97 probability, and delta p what we have got is 0.01. That 0.01 you are pasting at the output. Let us see what is this output in a while. We are pasting this 0.01 in this 3 cross 3 patch. Then with this we have understood what is the contribution of this particular patch or these particular pixel values in order to predict, for a prediction. Then we are going to stride it. When you stride, now we are taking this patch. Now, again we repeat the same, that particular patch values will be all 0. Then we are again seeing how it is having an impact. Then we are calculating the delta. Now, when you are calculating the delta p, you are getting 0.01. That 0.01 you will now paste it in this place. Now, when you paste in this place, you already have 0.01 here. Now, for that you will be adding another 0.01. So, you will add to an existing values, so that you will be getting 0.02, 0.02 in this place, and you will have 0.01. I hope this is clear to learners here. Then we will repeat this entire step. At one stage we will come to this particular patch. When you look into this particular patch, to that matter, when the patch comes here, when the patch is here, in this entire, definitely you will see that there is a good contribution. So now we have taken this particular patch. Therefore, that particular patch pixel values are all made 0. Now, when you pass this to an CNN model, you will definitely see there is a drop in the performance. So, you will see that the model is not very confident in saying that it is a dog, therefore, its performance is very less. When you have compared it with the ground baseline performance, the delta p value is very high. What is the delta p value? It is 0.56. That 0.56 value is placed here. Now, if you see when you place a patch, say for example, you have placed a patch here. You will be having some value. Again you will place a patch here. You will again get a value. When you get a value, when you add it to this existing, over a period of time, that entire portion is going to have a little larger values. So, which means you will see an output something like this. So, here what exactly we are trying to understand? We are trying to understand which are the pixel values which are actually contributing to this, contributing for prediction. So, this is called a saliency map, and if you observe here, there is one bias that we have introduced. What is that bias? Now, when the patch is here, when the patch is here and when you move, when you keep moving, there are some portion of the image which you will be looking into again and again. Corner pixel values you will be seeing only lesser time. So, obviously towards the end, when you look into this saliency map, which you are seeing again and again, those values, this delta value will be very high. So, this is a kind of a bias that we have introduced. Therefore, towards the end, once we calculate this, once we get this matrix, we have to normalize the matrix. So, how do we normalize it? Now, what output you have got, instead of taking such a huge matrix, let us understand, we are understanding this with a smaller matrix. Now, what is this matrix? This is all the delta p values that we have placed here. Now, for doing occlusion, whatever the patch size, here the patch size what you have considered is 3 cross 3. The same patch size you should consider even when we are normalizing it. Here, for a simple example, we have taken, for understanding how to normalize, we are taking an patch size as 2 cross 2. But otherwise, this patch size should be whatever the patch size we have considered for our occlusion operation. Now, when you look into here, how many times we are seeing these pixels? We are seeing these pixels one time. Right, all of these pixels are looked one time. Now, you will slide. When you slide, you are how many times you are looking into? This is looked the second time, this is looked the second time, this is looked one time, one time. Then again you have stride. When you have stride, this is looked the second time, this is looked one time, one time. Then you will stride down. This portion of the pixel values, this is the second time you are seeing, this is the third time we are seeing this is the first time, this is the first time. Then similar way, you will now increase this is looked one more time, this is looked one more time, this is looked one more time, this is looked one more time. Like this, if you repeat, you are going to see each of the pixels these many number of times. Can you see here? The first, the corner pixels are viewed only once, whereas the middle portion of the are looked more number of times. So this is something, a bias that is being introduced. In order to normalize this, this is not a correct way of saying which are the pixel values that are contributing. Therefore, we have to normalize it. How do we now normalize it? Now we have taken these values. Now you will take this 0.05, this is viewed only once, so you will divide it with 1, so you get this value. You will take this, which is 0.11, how many times it is viewed? It has viewed 2 times, you get this value. Then you will take 0.13, how many times that has viewed? It has viewed 2 times, you will get this value. So likewise, you take any value, you take this 0.32, how many times that has viewed? It has viewed 4 times, therefore you are normalizing it. Ultimately, this is the saliency map, which will actually tell us which are the pixel values which has contributed. Higher the value, higher that particular pixel value which has a pixel which has contributed for model prediction. So this is how we are going to normalize. So a quick revision of occlusion. We will first compute the baseline performance, then we will place the occlusion patch on the image, and you will replace it with either 0 or a mean pixel values. Rest of the image stays same. Then you are going to predict again on that particular occluded image. Then you will compute the delta. How is that you are computing this delta? What is the delta? Delta is importance of that particular patch for model's prediction. If the delta value is very large, then that masked region is important for a prediction. If delta value is small, the region is not important. Then you are going to stride it. Then you will once again get the next patch, then repeat the step 2, step 3, step 4. Then you are going to build a saliency map. Once you build a saliency map, we have to normalize it, because some patches have been seen more, some portion of the image has viewed more time, some portion has viewed less. In order to avoid this bias, we have to normalize it. Finally, whatever the heat map that we are going to get, that heat map shows which pixel values have really contributed for model prediction. So with this, we have come to an end of this particular session, where we have first started with why we require an XAI. Why do we require an XAI? Because the neural network is a black box model and it lacks the transparency. Because it lacks the transparency, it cannot be used for an high risk domains. Therefore, there is a need for an XAI. With the XAI, we can build a trust, ethical, fairness, AI system, which is highly accountable one. And then we have seen what exactly is explanation in XAI. The explanation, it mainly answers why do the model predict this. It identifies which are the important features and evaluates the model reasoning. And we have covered 2 XAI techniques. We have seen PCI and we have seen occlusion. How do PCI works? PCI, we are taking one channel at a time, we are going to shuffle the entire pixels, and then we are again calculating the performance, and then we are seeing, by comparing it with the baseline, we are seeing what is the importance of that particular channel in model's prediction. Second, we have seen occlusion, and what is occlusion here? Occlusion is we are taking the patch and we are seeing how much that particular patch is actually contributing for model's prediction. Takeaway is both the PCI and occlusion are model agnostics. The large drop in prediction, we say that the channel or region is important, and occlusion produces the saliency heat map. This will help in visualization, and it highlights which are the features which were influential in model prediction. So in the next session, we will be seeing the next two methods, which are SHAP and LIME, and we will see how they generate a feature importance for an individual sample. So, with this we have started with XAI. Thank you.